All right, so the next thing we're going to take a look at here is another principle that kind of ties into the movement of gases and some of the other concepts that we talked about previously. And this principle is known as Bernoulli's principle. And a lot of these principles obviously are named after people, scientists that came up with these, um, that made these observations in the past. And essentially what Bernoulli's principle says is that if you have a fluid, okay, we're gonna simplify this as much as possible. So for a fluid, and you can think of a fluid as a gas, so gases or liquids, for example, um, an increase in the velocity. Okay, and you think of velocity as analogous to speed. Velocity is speed in a particular direction. So an increase in the velocity of the fluid causes a decrease in the pressure. And then the the opposite would be true as well. So we'll say vice versa. And what that means then is that a decrease in the speed causes an increase in the pressure. All right, so it's a very simple principle, but it helps explain lots of things that we encounter, that we see and take for granted pretty much every day. So we'll take a look at a couple of examples, and then we'll try to tie it into gases and how they affect fire behavior. And we can tie it into things like air entrainment that we talked about previously. So if you think about if you're on a highway, driving a car, and you're overtaking, let's say, this truck, right? So you're moving in this general direction. Okay, truck and the car are moving in this direction. Um, what happens, I remember you're going through as you're driving, there's air all around us, right, in the atmosphere, and the car is buffeting against the air all the time. So when you are moving, both vehicles are moving in this direction. What happens is the air moves around the car. So for example, the air on the outside here, air moving around the truck in this direction. Now, at some point, there's a space between the car and the truck um, that is narrower, right? So this narrow channel here forces the air to move faster, right? So there's faster air movement between the vehicles as opposed to the outside of the vehicles. And you probably have encountered this, if you walk between two tall buildings, for example, on a windy day, you'll notice that the wind is a lot stronger between the buildings as opposed to anywhere else, right? And that's as the as it gets funneled through a narrower channel, the speed increases, the velocity increases, and according to Bernoulli's principle, that increase in the velocity causes a decrease in the pressure, right? So the pressure here on the inside or between the vehicles is low, so low pressure. And then we have higher pressure, relatively speaking, on the outside. So we have low pressure between the vehicles, higher pressure on the outside. And as you probably know, air, right, the general direction is air is going to move from high to low pressure, right? That determines and dictates all sorts of things from micro scale to macro scale. That's the reason why, you have weather systems that behave the way that they do. Air is moving from high to low pressure. So what this causes then, as air goes from high to low, it actually forces the vehicles, it presses the vehicles close to each other. So you probably experience this, you overtake a semi or something at high speed, and you actually feel the vehicles get sucked closer to each other. And that's because you create a little vacuum in between the vehicles because of that lower pressure due to the increased velocity of the air between them as it goes through that narrower channel. So that's very important because that observation we can use that and expand it to other situations to explain what's going on, right? So this is an example of Bernoulli's principle in action. So here are some examples of where Bernoulli's principle is put in action. So we use it, or not we specifically, but people use it to cause entrainment. We talked about entrainment before, where air specifically is pulled into a situation due to the movement of other gases. And we can use Bernoulli's principle here to explain air entrainment. So for example, in this first part A, this is in a Bunsen burner, for instance. We've used this in the lab before. Okay, so there's a nozzle here that controls the amount of gas coming in. And if we if we allow the speed of gas coming in to be high as it moves up here, it actually pulls in and it entrains the oxygen, the air specifically from the surroundings, and it causes then the right mixture of the air and gas to produce the flame, right? So the movement of the natural gas going through, as this speed is increased, you allow more of the gas to go in, it actually now sucks in some of the air through entrainment, because now as the gas goes through, the speed of the gases is high, the pressure is low inside here compared to the outside. So that forces then air to move from high pressure on the outside to low pressure on the inside. And that's what causes the air, which has the oxygen in it, to be entrained to mix with the gas. Something like this in B, this is an atomizer. So here you have a squeeze bulb, for example, and when you squeeze the bulb, that forces air to move out at a great speed. Okay, so air is moving out here, the high velocity of the gases in the air, and as the speed increases, the pressure decreases, and what that does is it actually now sucks out from the perfume bottle, in this case, some of these drops of perfume, right? So in this case, the drops of perfume are entrained into this stream of, whatever this puff of perfume is coming out. But it's taking advantage of Bernoulli's principle here. As you squeeze the bulb, the air comes out with high velocity, pressure decreases, it now sucks in. So a low pressure system, really what it does is it's like a vacuum. So it sucks in whatever is in contact with. In this case, it's the perfume bottle, and that's how you spray this perfume. All right. Similar things like paint sprayers, carburetors, for example, use very similar techniques to move their respective fluids. And the third one here in C, this is an aspirator that is used commonly to do lots of different things. And the principle behind this is the same. So here we have a stream of water at high velocity. So this is coming down. The water here is moving at high speed. So the fluid here is the H2O, the water coming in or coming through. This high-speed water creates a low pressure that now, if this is connected to the outside, the air gets entrained. So it sucks air in other words. And if you connect this to some other, with a hose, for example, to something else, well, then you have a suction on this side. Okay, and that's commonly used in this technique called aspiration. And that's used in things like suction pumps that people use in, if you go to the dentist, for example, and they stick that thing in your mouth to suck out all of the, all the stuff they spray in. That uses a very similar principle. For other types of pumps for, draining your basement or something, they work under a very similar principle. So the idea again is the Bernoulli's principle that relates the movement or the velocity of a fluid with a change in pressure, right? So the higher the velocity, the lower the pressure becomes, and that causes, in this case, air and other things to be entrained into that system. So imagine now that we had a room here with an opening and we had a fire burning in this room. Well, we've seen previously here that the hot gases are going to rise as they are less dense than the other gases around. And as the gases rise, they are going to move with a fairly high velocity. Okay, and as the velocity of the gases increase as they rise, guess what happens? You create now a low pressure created, again, due to Bernoulli's principle. And on the outside here, we're going to have a higher pressure in relation because we've just reduced the pressure on the inside. And air is going to move from high pressure to low pressure. So what you've done here is in this particular situation now, as this fire burns, okay, and the gases rise with a higher speed, it lowers the pressure, higher pressure on the outside. This entrains now air to come in due to the difference in pressure and actually now feed the flame even more, right? So we have, again, the principle being used to explain, Bernoulli's principle being used to explain why air is entrained in the first place, right? So difference in pressure causes air to move. How is that pressure difference created? Well, as the fire burns, these hot gases are produced. They are less dense. They rise with speed. And that difference in speed or that increase in speed causes a decrease in the pressure. That pressure difference, according to Bernoulli's principle, is going to entrain air now to come into this through this opening and then feed the fire, right? So we have lots of things occurring here, but if you go back to the principles we discussed, right, they all make sense in terms of what's happening on this small scale. But we can also, as we've seen before, use it to explain larger scale processes as well.